Okay, welcome back everyone. We got to the final session of today's event, and I thank you for being part of the With Turku event. Our next speaker is Christina Katsimerou. She studied electrical and computer engineering, and she got her PhD in computer science at Delft University of Technology. She is currently a senior data scientist in Booking.com, and she has been, in her current role, she has been applying machine learning to problems such as dynamic pricing and fraud detection. She has also formed a team that is currently driving the development of an experiment tool for scaling up experiments beyond A/B and causal inference. Christina, the floor is yours.
Thank you very much for the introduction. You can hear me fine, right? I will assume. Yeah. Okay, great, yeah. Cool. Good afternoon, everybody. Thank you for being still here, and thank you for the great talks. It was actually really a joyful day for me. So I am Christina. Yes, I am a senior machine learning scientist at Booking.com, and today my talk is going to be relatively technical. I will talk about a new experimentation framework that we are about to deploy at Booking.com. In the presentation, I will explain why I picked the name MAS, besides being a cool name. But very briefly, before I get into the topic, I'll just explain how I ended up in the Netherlands. So I'm originally from Greece. I am from Thessaloniki, a city in the north of Greece, where I did my studies, my undergraduate studies. Then I moved approximately 10 years ago. I'm also revealing my age here, to Delft, a cute little town in the south of the Netherlands, to do my PhD in computer science. And afterwards, it was an easy transition a little bit north to Amsterdam, where I joined Booking as a data scientist, and where I've been working for the last couple of years on a variety of projects. So many of you might, or some of you might have already used the website of Booking.com, maybe to book an accommodation for your trip, or to get any type of assistance for your trip. In reality, Booking is more than an accommodation website. It is an online travel website company with the mission to empower people to experience the world. This means that in the website, you can find pretty much a lot of aspects, hopefully all aspects that encompass our customers' travel. So you can find, besides accommodations, the flights, local transportations, attractions, experiences, and so on and so forth. Now, to make sure that we're actually providing helpful products and services to our customers to seamlessly experience the world, we need to listen to them with their data. And the way to do this is A/B testing. Now, every product, every tiny little feature in the website, every change in the customer service process, or every new machine learning model, before getting deployed to the millions of our customers, needs to first get A/B tested. I will be using the term A/B testing a lot, so I just want to clarify what it means so we're all on the same page. So A/B testing is basically a colloquial term for an online randomized control trial. So we have two versions, the version A and the version B, and then the online traffic gets randomly allocated to each of these versions. And then the version that is significantly better than the other in terms of some business outcome of interest gets deployed. So if every idea needs to be, so we are a big company with a lot of different teams, and if every new idea needs to actually first get A/B tested, this means that we have to run a lot of concurrent experiments on a daily basis. So yeah, as I say, here, more than thousands of experiments, which is a significant number. So in a way, it has turned into a way of decentralized decision-making tool. So everybody in the company, regardless of their background, if they have a hypothesis, they can run an experiment. And depending on the results of this experiment, they can also deploy it for all the customers. So this is actually pretty cool, very powerful as well. But of course, with power comes responsibility. So what we need to remember is that an A/B experiment is essentially statistical hypothesis testing. So there are some strict guidelines about how to perform this correctly. And the validity of the results depends strictly on whether people adhere to the protocol. Very roughly speaking, I will get, of course, into detail in the following about what exactly the protocol is, but basically people need to set up some parameters, an experimenter, to design the experiment. For example, what is the minimum effect size they need to see, or how long they should keep their trial going. However, often experimenters might make mistakes. They don't exactly misunderstand how to set up some of these parameters, or they forget, or they might get impatient. And of course, these accidents are they're accidents, and they are understandable because these people they don't really have the necessary statistical background to be able to understand how to properly run an A/B experiment. So that got us to realize that while A/B experimentation is a great tool for making decisions in a company, it can compromise seriously the validity if it is used strongly. So we need to probably try to improve it to make more rigorous, more robust to user errors, and maybe a bit more optimal so that we can make decisions even faster. So in the following, I'm going to use a specific example to explain a bit more what are the shortcomings that I see. First, I will explain what is the current way of running experiments, what are the shortcomings we see, and how we can address them with the max suggestion. So let's assume that we want to find an optimal website configuration. So we have different components there. We have destination, recommendations, accommodations, search boxes, and we need to position them around the page in such a way that the page is going to help the customer move forward to the next stages and eventually book. So we have the baseline, which is the current default version, and a couple of variants. So this is, well, a generalization of the A/B experiment that I described before. So it has, because it contains, it's an ABN experiment because it contains more variants, which is actually a very practical scenario to happen in a company. We have many hypotheses. So in this case, we have K independent hypothesis, null hypothesis. And for each of these variants, the null hypothesis is that it is significantly worse than the baseline, and the alternative that is significantly better. Now, what the user would need to do is set what is the minimum effect they want to see. And based on that minimum effect, they need to compute the sample size, the power calculation process, the minimum sample size that they need to have in their trial to be able to observe that effect size, to detect that effect size with a high probability. So this is the power of the experiment. At the same time, we also want to keep the false positives low. So we want to decrease the chance that you're going to see an effect when there is no effect. Typically, we fix this type 1 error, as we call it, to a low number, something like 10% or 5%. Just a little detail here, because we have K independent hypotheses instead of 1, we need to also account for the fact that we will conduct multiple hypotheses, and we need to decrease our significance threshold a little bit more per hypothesis to ensure that our family-wise error remains indeed at 0.1. This is a Bonferroni correction I've done here, but you can also do other corrections. That's just this is something that's taken care of by the tool, by the way, but I just wanted to get it out of the way. Now, after we know the sample size, then we distribute the traffic uniformly to each of these variants. We wait until n samples have entered the trial. And then in the end, we do our t-tests or chi-square tests, whatever. Let's say it's a binary metric. So we will compute the p-value for each of these hypotheses, for each of these variants. And low p-values are good evidence that the null should be rejected. So if the p-value for each of these hypothesis is lower than alpha, than our corrected alpha, then we deem these variants to be better than the baseline. That's how, this is pretty simple, pretty intuitive, and this is pretty much how experimentation works in a lot of companies right now. There are certain problems, though, with this. Some suboptimalities and some problems. So the first thing that is suboptimal is the fact that we need to sample uniformly. Now, let's assume that we actually know what the means of these variants are. So now here, imagine that I'm measuring, let's say, conversion. So each of these news here is the average conversion, let's say, per configuration. So in this case, the baseline is 0.1. The first variant is very close to the baseline. The second variant is much higher than the baseline, and the kth variant is much worse than the baseline. So with this information, it makes a bit more sense if I actually start sampling a little bit more towards the more promising variants So that would be the variant 2 that is more prominent for being the best one, and much less to the worst variants, and then maybe distribute the traffic uniformly between the base and the variant 1. Of course, the problem is that I don't know a priori what this means, and as a result, I do need to find a way to iteratively adjust my, my sampling as more data comes in. So this is a challenge. The second problem is that the users are not allowed to monitor. And what we mean by monitor here is that people would like to be able to view the results of the experiment as time goes by, and based on the results, decide whether they're going to continue the experiment or not. So why this is not allowed with this current setup is because we consider we're going to have one hypothesis, but if we are constantly conditioning on whether we're going to continue the experiment or not based on the previous data, we're conducting essentially multiple hypotheses, and we're not correcting for this in the right way. So actually, if I show you how the evolution of the p-value would look under the null hypothesis, so here I have a base and variant that are equivalent, equal to each other. So we're not supposed to see any effects, but the p-value is almost sure that at some point it's going to drop below a significance threshold. So here it actually drops 3 times. So if I were to pick the first time the p-value drops below the threshold and just deem the variant significant, I would really make a lot of mistakes. So this doesn't say that we shouldn't be doing monitoring. It does make sense that as the data comes by, they bring information, and I should not be ignoring it, but I would need to correct properly in a proper statistical way to be able to do this correctly without inflating my false positives. And then the third problem, but not definitely very important problem, is that the answer that I got from my testing was not the answer that I was looking for. So when I started, I said that I want to find the configuration that is the best. But what this multiple hypothesis testing returned to me is that the variant 1 and the variant 2 are significantly better than the baseline. But what I wanted to actually know is that the variant 2 is the best. This is to say that actually in business, we very often have different problems. So yeah, sometimes we want to optimize. We want to just find and deploy the best option, as we do, for example, with the website layout. In other cases, we might not even want to deploy a change, and we just want to learn, or we want to get inspired, or we want to combine the results that we get from an experiment with external data and see whether it fits in a bigger picture. So here, for example, the team wanted to add a new copy for the filters, and they just wanted to get inspiration, and they were interested in looking at all the promising variants that are significantly better than the control to combine them with some user research data. So in this case, we would be interested in seeing all the variants that are significantly better. And in other cases, time is of the essence. So we just want to be very quick with a decision. Maybe we don't have the time to wait until we figure out that a variant is the best out of all. We just need to get anything that is better than the baseline. This can happen because we're quickly solving pain points. We have a deadline. Maybe there are bugs. Maybe for any reason, we need to make a fast decision making. So here, we would just need to take any arm that is significantly better. However, now, with all these problems, though, at the moment, despite of these different business problems, people can get a specific answer that the tool is giving to them. So this is essentially a pretty big problem, because everybody needs to start thinking in terms of what the tool outputs to them, but this is not what a measurement tool is for. So for all these reasons, we took all these problems together, and then that's what we hope that we are addressing them with the MASS experimentation framework, which stands for multiple problem, multiple hypothesis, adaptive sampling, and stopping. And I will give you a little bit of more, a little bit of a flavor about how we get inspired to solve these problems. And the main inspiration for the solutions comes from the multi-arm bandit literature, specifically for pure exploration. Some people, or maybe most people, are more acquainted with bandits for reward maximization, in which the task is that I want to find the particular variant or the particular arm, I will be using them interchangeably from now on, that will maximize the cumulative reward. Now, because we want to maximize the reward here, or minimize regret, our policies need to very carefully balance between exploration and exploitation in order to be able to achieve that objective. However, in our case, we don't really have any reward constraint. We're going to run the trial for a finite period of time, and then the best solution is going to be deployed for everybody. So there's no really cost in exploring. In fact, we just want to explore. We just want to learn the statistical properties of our arms. So that's exactly what pure exploration does. So pure exploration is a statistical hypothesis testing, which gathers all the characteristics that we're looking for. So it's multiple. Composite. Composite means that we don't know exactly what the alternative is. Sequential, that means that we can stop adaptively on data-dependent moment. And active, that means we can sample as well adaptively. So each of these components fit exactly very nicely into all the challenges that I described before. And now within this pure exploration problem, we can define like these sub-problems that you can also map to the business problems I talked about earlier. So the best arm identification, in this case, I'm looking for a second arm. If I start counting from the 0, all arms better than the control. In that case, I would like to see 1 and 2, or any arm better than the control. In that case, either arm 1 or 2 would do. So for all these problems, the objective is that I want the algorithm to return the correct answer to me, keeping the error low. Usually we pick a delta which is 0.1 or 0.05, and as fast as possible. So these are the constraints. Now I will describe a little bit about how the adaptive sampling and stopping would work, specifically for the best arm identification problem. There are similar ideas could be applied for the other problems, but the other problems are not solved yet. So I will tell a bit more later about that. Now, let's say that we want to sample adaptively. We could find a lot of heuristics actually to do that, to adjust the sampling based on the problem that we want to solve. But there's one optimal way to do it. The idea is that if we know if we know the model we're working with, that means we know the distribution where the model comes from. So let's say it's a binary variable, and I know the means of each of the arms. Then there is an optimal way to sample. And actually, this optimal way in this particular example matches the intuition that we had. So here, the optimal way to sample from our example is I need to sample 40% the best arm, 2% almost practically not at all the worst arm, and around 29% equally the baseline and the very close variant it has. However, again, we do not know these averages, so we need to estimate this means. So we need to do this. We need to be able to work with data as it comes. So therefore, we need to use an algorithm that can actually guarantee that we will converge to these optimal sampling proportions with more data. So the algorithm works as follows. So it computes actually these proportions based on the empirical means that we have observed. And then with the right exploration, it is guaranteed that we will converge to the empirical proportions, to the optimal proportions, sampling proportions. So here I'm actually plotting how these proportions would look over time in such an experiment. So you could see that already the W2, which is the second variant, the best, and the worst, the W3, the algorithm already converged pretty soon to their correct values. It had a little bit more trouble distinguishing between 0 and 1, but eventually it did. So this is approximately how over time the algorithm learns how to sample optimally with the data. Of course, if the problem was different, if it was all better arms identification or any better, then we would use a similar approach, but then these optimal proportions would actually be different depending on the problem. And of course, we also need to find a way to stop. So here the idea is that how can I, observing the data, find the right moment to stop without inflating my false positives? This is a non-statistical question. Dates back, and this solution dates back to the 60s with Chernoff, actually, with a generalized likelihood ratio test, which is used basically for sequential testing. So the idea is that we now want to construct a test statistic over time and to stop when there is no plausible alternative model in which the correct answer that we're returning is actually wrong. So specifically, this is a log likelihood. This ratio basically represents the maximum likelihood that the data we have observed so far comes from a model where the reported answer is the correct answer. X here would be the data we have observed so far. And it's divided by the maximum likelihood that the data comes from a model in which that answer is not the correct, the reported answer is not the correct answer. So you can imagine a different model where the second variant is not the best now. So with this definition, if we are pretty sure that our answer is correct, it means that it's very likely that the data comes from the correct model. So when the GLR statistic is large, then we want to stop. But how large should it be? We don't want to be very conservative, because then we're not going to make a lot of mistakes. But at the same time, we also want to be able to stop as early as possible. So there has been a lot of work, including recent work, about trying to find a tight threshold that depends on time and on the number of alternatives and the significance and the confidence parameter. But so as to not to minimize the runtime or the sample size, but while actually guaranteeing that the error rate will remain low. So here you see in the plot, I have plotted both the threshold and the GLR statistic, and both you see that they change over time. So when these two meet, then this is the moment that we're going to stop. This is actually nice because this now allows the user to pick. They can check the experiment beforehand, before its termination. Of course, we don't risk anything because before its termination, there is no answer reported. So we're not risking inflating the false positive. And they can decide that they didn't find the effect they wanted to see, so the experimenters can actually stop the experiment. Another good thing is that, of course, we can plug it in different algorithms, so it doesn't have to be coupled with an adaptive sampling. We can also use adaptive stopping with uniform sampling. However, if it's used coupled together with the optimal adaptive sampling, then we're also guaranteed that we're going to finish the experiment very quickly. Now, as I already mentioned earlier, so the best harm identification problem is a well-studied problem, especially in the last decade. So the optimal solutions exist for that. However, for the other two problems, they're quite recent. So we already submitted a paper on the all better arms than control problem, and we're working on the any better arm problem. And probably there are many other problems, so it's going to be an interesting additions for the future. So to solve these problems, we work together with some leading researchers in the field from Amsterdam and France. And we are excited to see what's coming next. If I can summarize, we're using all these insights from the research to basically provide an experiment tool that is more optimal in terms of runtime. So it can run faster, it can finish faster because it uses adaptive sampling and stopping. But at the same time, it releases the user from the burden of having to design the experiment and decreases the chance as a result that we're going to have mistakes because of the users. So now there's a lot of freedom for our experimenters to run experiments without risking making mistakes. They can pick, they can stop earlier, and they can get the right answer to the problem without having to tweak their business problem to what the experiment tool can give to them. Hopefully this can give inspiration to maybe others as well to improve their experimentation platform and help their users. This was my talk. I'd be happy to have questions either here or to connect also and have a discussion later or email or in LinkedIn. Thank you.
Thank you very much, Christina. Is there any question from the audience, either in Q&A or does anybody want to talk? I think they probably need some time to process.
Yeah, it's a little bit, I feel it's a bit more heavy.
Yeah, but it was very interesting, and you find a very comprehensive solution to a difficult problem. So you're ticking a lot of boxes in that sense with your solution.
That was the final, that was the idea, to answer yes to all the, to pick carefully each of these entries.
Yeah, that's true. Thank you very much. I think we can move to our next as our final